Hi everyone, I'm Yidi. First, let me help to give you a brief introduction about our ME231A final project. Our project is about performance of MPC, LQR, and briefings on rocket landing problem. We got 4 team members. At the beginning, when we decided to do a project together, we had a lot of different project ideas about MPC, like autonomous parking, controlling a train, or rocket landing. As for the reason why we select the rocket problem, that is because all team members wanted to do and create some cool stuff. Besides, some guys are huge fans of SpaceX and Elon Musk, and others have dream of becoming an astronautic engineer. Finally, we made up our minds to solve the rocket landing problem. The contents of our presentation can be divided into 6 parts, which is introduction, rocket model, experiments, simulations, results, and conclusion. Next, I want to introduce our team members. Haoyuan and Yidi are ME students from ME department and concentrated in product design. Jiakai is also ME student in ME program, but his track is control. Last, Guangzhao Yang is in his final year of master degree from EECS department, and his concentration is robotics and automated system.
So here's the rocket model without grid fins. Since this is a 2D model, we have 4 states in total: the rocket angle theta, the rocket angular velocity omega, the rocket height h, and the velocity v along the z-axis. And we also have 2 inputs, and those are the thruster force F and the thruster angle delta. We discretize the continuous model by applying small angle approximation to the thruster angle delta, and linearize the model by substituting Fk times delta k equals to U tilde k. And next, we model the rocket with grid fin by adding the drag force as shown in the slides. S of t is the grid fin's projection area onto the x-axis at different time t. The drag force here will affect rocket angle and rocket angular velocity and also help reducing the landing velocities. And we cannot really linearize this rocket model with grid fins simply because the states and input are coupling together and cannot be separated. Moreover, we think that we cannot apply small angle approximation to the theta, which is the rocket angle, because unlike the thruster angle delta, theta is not necessarily a small angle. And finally, we add the vertical drag force as an external disturbance along the z-axis and the horizontal wind force as an external disturbance along the x-axis. We want to explore which one of the LQR or the MPC controller is better at rejecting these disturbances.
We want to compare the performance of MPC and LQR controller in this rocket landing problem. Here is the criteria of comparison. We want to investigate the landing time, landing posture, angle correcting time, and the ability to reject the disturbance. First of all, we design an MPC controller to land the rocket vertically with 0 speed and 0 angular velocity in the end. We set the state constraints, input constraints, and code function, then solve the optimization problem via FinalProject solver. Then we plot the states and inputs, and then obtain the landing animation. Moreover, we design a state feedback LQR controller to achieve the same goal by tuning the relative weights, which are Q and R. Also, we set the input constraints, but this time there's no state constraint anymore. Then we set up the landing simulation as well. Here is the figures. You can see in the figure, the MPC landing process has less landing time than LQR. Also, it has precise 0 landing angle to make sure the rocket can land vertically. On the contrary, the LQR landing process cannot even make the angle of inclination 0 in the end. Then we introduce both vertical and horizontal disturbances to these 2 models. As you can see, the MPC has better rejection of disturbance than LQR. It can react to the disturbance immediately and maintain the real states as the desired ones. All the animations are shown in the end of the result part.
To compare the performance of rocket models with and without griffins, we compare the two models under two scenarios, which are with disturbance and without disturbance, and we will evaluate the performance according to these criteria shown here. So this is the simulation results of rocket model with griffins without disturbance using MPC controller. Compared to the simulation results of rocket model without griffins, we found that the model with griffin requires lower thrust force all the time, which means the use of griffins helps reducing energy consumption. And this is the simulation results of rocket model with griffins with disturbance. Compared to the simulation result of the model without griffins, we found that not only the energy consumption is improved, but also the disturbance resistance is improved. We found that the model with griffins can fastly respond to disturbance and correct its body posture. Here is the animation video of all simulation results. From the first and second video, we can clearly see that the LQR controllers fails to land the rocket in a vertical posture, whereas the MPC controller did a great job in adjusting the rocket posture and land the rocket successfully. From the third video, we can see that the rocket model with griffin has fast response to wind disturbance and is able to adjust its body quickly and land the rocket in a vertical posture successfully. From these simulation results, we found that the MPC controller is always better than LQR controller since the LQR controller fails to land the rocket in a vertical posture. And in terms of disturbance rejection, the MPC could respond fast and adjust its rocket body to the desired posture under disturbance scenarios. Besides, it is also found that the rocket with griffins are more energy saving and it has a faster response to disturbance than normal rocket models. So in conclusion, the MPC has better disturbance rejection performance than LQR controller, and adding griffin on the rocket is helpful in terms of energy saving.